Hello, everyone. I'm Paul Jensen. I'm here to present our work beyond cosine decay on the effectiveness of infinite learning rate schedule for continual pre-training. This is joint work with my colleagues Vaibhav Singh, Paria Mehbot, Adam Ibrahim, Irina Rish, Eugene Belilovsky, and Benjamin Therian. So uh, currently, foundation models are becoming ubiquitous. So we are using ChatGPT, Gemini, and VO, and all those models in our daily work uh, to generate emails, reports, and code. As these models become ubiquitous in our life, it's very important to keep them updated such that we can improve their capabilities in new domains. So the challenge is world keeps generating new data and new data sets become available. So the foundation models need to adapt continuously to new data sets. For example, in language modeling, you might have access to English data set, and over the time you will get access to the German data set. And then you will get access to a code data set. So this keeps happening. So the current method that's successful is to retrain the model from scratch by combining all these data sets. So that is more costly. And as we saw in recent events, sometimes people might not like the new model that comes. So it's very important for us to train the model with new data sets continually without without retraining it from scratch. Consider this scenario. You have a data set and you train your AI model and you have your users. And when they are using your model, you get access to new data sets. So the goal is to deploy the best model for users and keep training on new data sets without forgetting previous tasks. So, and we have to do this efficiently with a low cost. So in foundation model pre-training, cosine schedule is the gold standard. We have, in the initial phase, we do warm up from a very low learning rate, and then we decay the learning rate using this function. And we decay the learning rate to near zero values at the end of the training. For doing this, we need to start with the number of training steps that we are going to do. So in language model pre-training, it's going to be the total number of token budget that you are going to allocate for your training. So this cosine schedule is widely adopted in large-scale pre-training of foundation models, especially because it smoothly decays the learning rate from its initial value to near zero. We will have high learning rate and low learning rate smoothly changing from start to the end. So this helps to stabilize training and improve the final performance. But it has its limitations when it comes to continual training. The problem is we require predefined training duration at the start of the training. So this inherently limits the amount of training that you are going to do. So at the end of the training, you will end up with a very low, near zero learning rate. So you cannot continue training on new tokens when you get access to it. So you have to do rewarming. And in the previous work by Ibrahim et al. In 2024, they found this rewarming phase causes significant forgetting in the previous data set when we do it on when we do the rewarming in the new data sets. And also, it limits the flexibility of training and performance degrades when we have like strong distribution shifts. So so in Ibrahim et al. 2024, they introduced infinite learning rate schedule. So the main innovation in infinite learning rate schedule is that It has a constant phase. So it starts similar to cosine schedule. We have the warm-up phase, and then we have a cosine decay phase. But instead of going to a near zero value, we go to a constant learning rate, and then we keep on training with that constant learning rate for a while. When we hit our token budget at the end of the training, we quickly decay the learning rate to a very low value. Here, due to this flexibility, we can save two checkpoints. One is the pre-annual checkpoint that's be saved before the start of decaying, and then we can have annual checkpoint at the end of the training. So this annual checkpoint during the annealing phase will quickly decrease the loss on the current data set, and we can use this annual checkpoint for deployment. So that will be the best performant model for the current task, and that will be useful to be deployed to the users. And we will have the pre-annual checkpoint that's trained with the constant learning rate, and then we can keep on train to the new data set with that constant learning rate. So at the task 2, we can do the similar thing. We can train with the constant learning rate and have the pre-annual checkpoint, and then do the decaying on the current data set and deploy that and keep the pre-annual checkpoint, and we can keep on doing for new data, new tasks that we are adding. So here we are introducing two hyperparameters. One is the constant proportion. We need to decide how long the constant phase is going to last. And also, we need to decide the constant learning rate that we are going to decay into. So the key question is, how does this infinite learning rate schedule perform under strong distribution shifts? To find that, we conduct experiments across 3 different scales. First, we do it in a much smaller scale. We do MAE pre-training in CFAR 10. We do the MAE pre-training, and then we measure the linear probe accuracy on that task. And then we move into larger scale in vision pre-training, where we go from 3 different data sets. We first train it on ImageNet, then Places, then fire risk data set. In the third scale, we go to language modeling. That's we train on DCLM, Stack, and German data set. So in the CFAR 10 MAE pre-training, that's a very small scale experiment. That so we did this to have a simple setup that to compare it with most continual learning baselines. We use a VIT tiny model with 5.8 million parameters. So here we use a class incremental setup. We have different subsets of the classes, and we introduce them, and we do MAE pre-training at each point, and we freeze the encoder and then find their linear probe accuracy. So in the CFAR 10 MAE pre-training, we found that compared to continual learning baselines that we use, like standard fine-tuning, sequential fine-tuning performed better. This is partly due to when we introduce experience replay, we found that the model tried to overfit to the buffer, since here the data set size is very small. And also in the other cases, it tried to be more stable than plastic. So when we use infinite cosine schedule, it's standard sequential fine-tuning, and with infinite learning rate schedule, we found we were able to get 1.87 average accuracy increase over the baseline in no replay training, and 4.22 average accuracy increase over the baseline in 50% replay training. So in the 50% replay training, we have we replay the 50% of the previous data sets when we train the new data sets. So this we use very large buffer sizes because for ME pre-training we need more data, and even in the CFAR10 it's already a smaller data set. So then we move on to the important part of our study. That's the large-scale ME pre-training. So here we do the practical scenario where we have access to first data set, that's the full ImageNet, and then we go to places and satellite imagery, that's the 5-risk data set. So ImageNet, it's 1 million data sample pre-training, and then that mostly consists of objects, and then we in the places we have different scenes, and in the 5-risk we have different satellite images. So this is a strong distribution shift. Here also we measure the linear probe performance after each task, and we perform the we measure the performance on all the previous and new future tasks as well. Here we use a VIT Bayes 86 million model. So when we see, so here after training on each data set, we measure the performance on all the future and current already seen data sets. So with replay, we found that infinite learning rate schedule is able to achieve better average accuracy, and also especially it's even more capable in preserving the first task performance. It has similar performance in the final task. We can see it in when we compare the cosine and infinite schedule. It's 61.13 and this is 61.5. But it preserves more of the previous task performance. So another important observation, it's preserved the task performance even without replay. So even in the without replay case, we have 15.06 forgetting compared to cosine, which has 17.91% forgetting. So as I said before, we are introducing two new hyperparameters in this scheduler. So we have to do analysis on how to select that constant learning rate and the constant proportion. So here we found that with a lower constant learning rate of 3.75 E-5 and longer constant proportion of 0.5, we were able to obtain best performance on the previous task. So we select these values by finding the average of maximum and the minimum learning rate that we have in the scheduler. We selected one value above the average and one value below the average. So and then we go to we scale up this experiments to LLMs. We train Llama 3 style 570 million parameter model continually. We had the token budget of 100 billion tokens on each data set. And here we assumed that the tokenizer vocabulary covers all the domains, and we didn't do any tokenizer analysis. So when we scale up to the LLMs, we found that the infinite learning rate schedule is better in preserving the previous task performance. That's consistent with vision experiments as well. Here also, without replay, we found that we need to select a lower constant learning rate, that's 1e negative 4, and a longer constant proportion of 0.6. So when added with replay, we found a slight mismatch in the selecting constant learning rate. So here we have to select 2e negative 4 as the constant learning rate, and the constant proportion is still 0.6. That was the better value to select. So in the language modeling case, we added another third distribution shift. First is DCLM, which is English data, and then the stack, which consists of code data, and the third distribution shift is on German data sets. So this shows from English language to code to German language. Even with 3 distribution shift, we found that infinite learning rate schedule is capable of preserving the previous task performance. So here, this is without replay. So the value that we selected for the constant learning rate 1e negative 4 is consistent. Then we did analysis on the common benchmark language modeling benchmarks. Here we note that we didn't do any instruction tuning, so we just tested the base model, and we found that our DCLM to stack with 50% replay performed the best on the average on all the language modeling benchmarks. So from all our experiments, the hyperparameters, we give some tips on how to select these hyperparameters. So without replay for both MAE and language modeling pre-training, we found that we need to select lower constant learning rate than the average of max and mil LR. And we need to select longer, it has to be longer constant phase. And with replay, for MAE pre-training, we need to select the lower constant learning rate, similar to without replay case, but for language modeling, we need to select something like higher constant learning rate. So in our work, we know some limitations. One is even though we provide some rules of thumbs to select the hyperparameters, it's always better to do hyperparameter tuning to get the best performance. And we don't do any tokenizer analysis. We say that the Llama 3 tokenizer is able to capture all the domain, and if it isn't, then the tokenizer will become the main bottleneck. And we didn't do any experiments on diffusion models. So as future works, there is a lot of chance to do theoretical analysis and find why it works, and to develop more principled approach for hyperparameter finding. And we can add more distribution shifts and see how it performs when we increase more tasks that we need to shift. I thank all my collaborators and supporters, and special thank for Oak Ridge for the computational support. And I thank CoLLAs for providing this opportunity. Any questions?
Yeah. Oh, thanks. Are you for the cosine? Are you doing it per task and then rewarming it? Are you doing the rewarming?
Yeah.
Okay.
So
I was checking to see if the rewarming was happening. Otherwise, I was like, well, this seems pretty Could be unfair here.
It's similar to here, like
Yeah.
when we
gotcha,
go to the
gotcha,
new task.
Gotcha.
I was wondering, a lot of time in continual learning, you might not know how long your task is. Like you couldn't do this annealing with knowledge of like how long the task is. Have you looked at, I don't know, how to schedule the learning rate in this situation?
Sorry, I didn't get it. So
Like your learning rate scheduler assumes that you know how long your task is going to be, like how many data points.
for the current task, we know how long we are going to train.
Yeah, but I'm saying there's lots of situations where that's not the case. Do you know? Well, have you thought about how to sort of do this like annealing in those sort of cases?
Yeah. So in our focus, like we only focused, like main focus is on the language model. So in language model, like people know how long they are going to train because of the budget. But that's an interesting thing to study. Like if we don't know how long we are going to train, currently we don't know when to start the annealing. So mostly we select the last 10% of the training to do the annealing. But if we don't know, currently in our work, we don't have anything. So it's an interesting future work to try.
Thank
Thanks.
Hi, thanks for your talk. I'm wondering if you've tried other infinite learning rate schedules. So something like inverse square root with cooldown.
Yeah, so in the current one, we did only the cosine schedule, but we also tried inverse square root as for the cooldown phase, but it didn't perform well in both cases. So that's why we didn't like went with it.
Sorry, you said for the cooldown phase, you use the inverse square root?
Yeah, from after the warm up, we experimented with inverse square root rule.
So for the whole schedule, you tried inverse square root, not just the cooldown, just to clarify.
Only for the cooldown phase.
Yeah, so I was referring to the basically after warm up, use the inverse square root schedule because it'll have a similar property to your sort of constant phase where you stop at a, let's say, eta constant, and then you do a cooldown, which is similar to what they do, right?
Sorry.
So you typically, in the inverse square root schedule, you define like a inverse square root after you warm up. And so you degrade until essentially it starts to flatten out. Not exactly flat like you're doing here, but it has a similar property. And then you do the cool down phase separately. This is from Lucas Bayer's scaling vision transformers work.
So it's the infinite scheduler is from the scaling vision transformers work. So it's